November 14th, 1940. A black, ice-flecked sky, 15 zone feet above the English Channel. The cockpit of the Bristol Beaufighter is a universe of cold vibration. Flying Officer Alistair Finch grips the yoke, his knuckles white inside fleece-lined gloves. The twin Bristol Hercules engines are a deafening, oscillating roar that he feels in his teeth. He smells the tang of hydraulic fluid, hot oil, and the faint, sour trace of his own fear. Outside, there is nothing, not a star, not a flicker of moonlight on the churning water below. There is only the absolute, smothering blackness of a nation under blackout. Finch doesn't fly a plane. He flies his instrument panel. The artificial horizon, the altimeter, the airspeed indicator. These are his only reality. A sharp burst of static crackles in his ears. Vector flight, Tide callsign Warlock. Bandit bearing 090. Range 6 miles. Angels 15. Finch keys his mic, his throat dry. Warlock, Roger, no joy. He strains his eyes, pressing them against the freezing perspex, desperate for the silhouette of the Heinkel He-111 bomber that the ground radar station swears is right in front of him. 6 miles. At their combined speeds, that is less than 2 minutes. The ground radar, part of the legendary Chain Home system, is a marvel. It uses colossal 350-foot towers on the coast to bounce long, sweeping radio waves off distant targets. It saved the RAF in the Battle of Britain by daylight, but at night it is a blunt instrument. Its resolution is measured in miles. It can tell Finch where the bandit is, but it cannot guide his guns. The system is called ground-controlled intercept, but it feels like a game of blindfolded archery. Warlock, he's turning, now bearing 085. Range 4 miles. Do you have him? The ground controller's voice, a young woman's clipped, anxious tone, sounds impossibly distant. Negative, Vector. Negative, Joy. Alistair snaps, his frustration boiling. The sky is black. Where is he? He scans the dark, his heart pounding a rhythm against the engine's drone. He's hunting an invisible enemy, guided by an imprecise echo. He can almost smell the German bomber, the diesel fumes, the exhaust, but he sees nothing. His Beaufighter is a predator with no eyes. This is the failure of 1940. Britain controls the day, but Germany owns the night. The Blitz is raging. Coventry, just days ago, was eviscerated. Tonight it is London's turn. Warlock, range 2 miles. I think he's right on top of you. The controller's voice is strained. Suddenly, a new sound cuts through the engine noise, the hollow thump, thump, thump of anti-aircraft fire far below. The flak bursts paint the underside of the clouds in brief, useless flashes of orange. The bomber has passed him. It is over the coast. It is heading for the city. Finch banks his heavy fighter hard, a useless, enraged gesture, pulling G's that press him into his seat. He has failed. The technology has failed him. He is a knight in armor, but he is blind. The ground controller comes back on the radio, her voice flat, defeated. Bandit is over the target area. Return to base, Warlock. Alistair eases the yoke back and turns for home, the distant, hellish red glow of London's fires reflecting on his wing. He and thousands of other pilots are fighting a new kind of war, a technological war, and they are losing it every time the sun goes down. They are desperate for a miracle. They need to put eyes into the dark. What no one knew, not Alistair in his freezing cockpit, not the controllers in their concrete bunkers, was that this moment, this agonizing blindness, was about to be cured by a revolution boiling in a university laboratory, a revolution that would change the war forever. The problem is one of physics. The year 1940 is a bottleneck of innovation. The Wizard War, as Churchill calls it, is a desperate race of wavelengths and frequencies. The core of the issue is this: Britain's chain home radar, the system guiding Alistair Finch, operates at a long wavelength between 10 and 50 meters. To generate these meter waves, the transmitters are gargantuan. The 350-foot steel towers lining the coast are, in fact, the antennae themselves. This system is brilliant for early warning. It throws a wide, coarse net across the sky, detecting large bomber formations from 100 miles away. But its resolution is appallingly bad. The beam is so wide that it cannot distinguish between one bomber and 20. It cannot tell their altitude accurately. And, most importantly, the equipment is far too large to ever fit inside an airplane. What the Air Ministry craves, what the Royal Navy needs to hunt U-boats, is a different kind of radar. A radar that operates on microwaves, wavelengths not of meters, but of centimeters. A 10-centimeter wavelength radar would have a beam so sharp, so precise, it could paint a single bomber in the sky. It could detect the tiny, fleeting target of a U-boat's conning tower or periscope slicing through the Atlantic waves. A 10-centimeter radar would be small enough, its antenna a compact dish, that it could be nestled in the nose of a bow fighter or slung under the wing of a coastal patrol bomber. It would be the miracle. It would give the night fighters eyes. It would illuminate the U-boat, stripping away the nighttime invisibility that is its greatest weapon. But there is one insurmountable obstacle. To generate a high-power microwave beam, you need a special kind of vacuum tube. A transmitter. The best, most advanced device available in 1940 is the klystron. Developed in America, the klystron is a complex and delicate instrument. It works by shooting a linear beam of electrons through a series of resonant cavities which bunch the electrons and generate a radio wave. The klystron is a scientific marvel, but for the war effort, it is a catastrophic failure. It is fragile, it is unstable, and crucially, its power output is pathetic. The best klystrons in the world, the product of years of research at top-tier labs, can generate, on a good day, perhaps 10 or 20 watts of power. To be militarily useful, a radar needs kilowatts, thousands of watts. It needs to scream a signal miles into a storm and catch the faintest whisper of an echo. In the secret research facilities at places like GEC, General Electric Company, engineers are despondent. They try to scale up the klystron. They increase the voltage, but the device just melts. They try different cavity designs, but the beam becomes unstable. The consensus in the Air Ministry is grim. The shipping losses in the Atlantic are mounting. 400,000 tons are lost in a single month. The cities are burning. The existing meter-wave radar, the AI Mark IV fitted in some fighters, is so clumsy and short-range it is nearly useless. Pilots joke that they must be able to see the bomber before the radar can. The problem of high-power microwaves is deemed a long-term project, something for 1944 or 1945. It is a technological brick wall. Experts agreed. It could not be done. The solution comes not from the government's massive, well-funded research centres, but from the physics department at the University of Birmingham. The department is led by an energetic Australian physicist, Mark Oliphant, who has pushed his staff onto war work. Among them are two men who could not be more different from the image of military saviors. They are John Randall and Harry Boot. Randall is a quiet, reserved academic, a man in his mid-30s whose pre-war specialty was the fluorescence of glass. Boot is his younger colleague, a brilliant, practical-minded graduate student, a man who knows how to work a lathe as well as a slide rule. They are, in essence, university researchers, not government weapons developers. They have been assigned the impossible task: find a way to generate microwave power. They review the existing technology. They study the klystron and, like everyone else, find it wanting. It is too complex, too weak. They are frustrated, staring at a problem that has defeated the world's best engineers. They dig through old physics journals, searching for any alternative, and they find one. A scientific curiosity, and also ran from the 1920s, called the Magnetron. Invented by American Albert Hull, the original magnetron was a simple vacuum tube with an anode and a cathode placed in a magnetic field. It worked, but it was wildly inefficient and produced very low power. It was considered a dead end, a footnote in the history of electronics. Randall, the theorist, stares at the diagrams. In the klystron, the electron beam is linear. In the magnetron, the magnetic field forces the electrons to travel in a curve. This is the key. But why is it so inefficient? Because, he realizes, the resonators, the part of the tube that actually creates the radio wave like a tiny organ pipe, are on the outside of the tube. The energy is lost. A thought strikes him, an idea that is both crude and brilliant. "Harry," he says, his voice quiet, "what if we stop thinking about the klystron? The klystron's resonators are delicate, cavities. What if we take the power of the magnetron's anode and combine it with the concept of the klystron's cavities?" Boot looks at the sketch Randall is making. It doesn't look like a vacuum tube. It looks like a solid block of copper. "What is this, John?" "It's the anode," Randall says, sketching faster. "A solid block, and we drill the cavities of the resonators directly into the block itself." He draws 6 small holes arranged in a circle, connected by slots to a central chamber. The electrons will spin past these holes, like blowing across the top of a bottle. The entire block will resonate. It will become the transmitter. Boot is skeptical. "John, the heat, a solid block of copper, it would melt. The math to make it resonate. It's guesswork." "How many cavities? What shape?" "We'll guess," Randall says, a strange fire in his academic eyes. "It's not delicate, it's brute force. It will be a furnace. If the electrons resonate, the power will be immense." The idea is absurd. It breaks all the rules of elegant tube design. It is less a piece of electronics and more a piece of heavy plumbing. It is a crazy idea. But Oliphant, their boss, is desperate enough to give them permission to try. With the university workshop at their disposal, they decide to build the thing themselves. They have no high-priority funding, no specialized parts from government suppliers. Randall and Boot must scavenge. They move into a small, grimy laboratory, the air thick with the smell of ozone and hot metal. They find a massive magnet, once used for other experiments, and wheel it into place. They need a power supply. They lash together transformers that fill a wall, capable of delivering thousands of volts, and for the device itself, they go to the university's main workshop. They hand the baffled technicians a simple blueprint, a solid, hockey puck-sized block of copper with 6 holes drilled through it to form the resonant cavities and a larger central hole for the cathode. It is simple, almost primitive. The technicians mill the block. Randall and Boot assemble it. They need to make it a vacuum tube, which means it must be perfectly sealed. They have no advanced glass-blowing equipment. Instead, they use plates of copper and seal the joints with red sealing wax, the kind used for letters. It is a device built of brute force and office supplies. They bolt this copper anode block between the poles of the giant magnet. They connect the water-cooling pipes as they fully expect it to melt. They are ready for their first test. It fails. They turn on the power. The vacuum pump hums, the voltage climbs, the cathode filament glows, and nothing. A small spark. The sealing wax cracks. The vacuum is lost. They get a flicker of power, a few watts, and then silence. They are despondent, but not broken. They knew the wax was a gamble. They regroup. They spend a day meticulously resealing the joints, baking the device in an oven to drive out all the moisture. They try again. It is February 21st, 1940. The room is tense. The only sounds are the hum of the transformers and the hiss of the water pump. Boot stands at the control panel. Randall watches the device, crouching behind a crude safety screen. "Power on, Harry," Randall says. Boot nods. He slowly turns the knob. The voltage climbs. 100 volts, 500, 10,000 volts. The ammeter needle jumps. The magnet whines with an ungodly force. Suddenly, a small neon indicator bulb lying on the bench a few feet away flashes. "John," Boot says, "look, they increase the power. The neon bulb doesn't just flash, it glows with a fierce, steady light, completely unconnected to the circuit." Randall grabs a long fluorescent tube and holds it in the air, near the output antenna. It instantly lights up in his hands, bathing the dim lab in an eerie white glow. The air crackles with energy. "My God," Randall whispers. They try to measure the output. Their instruments are incinerated. The power is beyond anything they have ever seen. They scramble for heavier-duty equipment. They do the calculations. The klystron produced 10 watts. Their crude, wax-sealed copper block is generating 10,000 watts. 10 kilowatts of power. And it's doing it at a wavelength of 8 centimeters. They have done it. They have created the miracle. They have built a microwave furnace. The room is hot. The smell of ozone is overwhelming. But they are staring at the device that will win the war. If you're hooked on this story, hit that subscribe button. Mark Oliphant is stunned. He sees the test and immediately calls the Air Ministry. The response is at first disbelief. When Randall and Boot are summoned to London to present their findings to the main government radar committee, they are met with open skepticism. The room is filled with the country's top electronics engineers, men from GEC, who have spent 2 years and a fortune trying to perfect the klystron. In walk 2 provincial academics, carrying a heavy copper block that looks like a paperweight, sealed with wax. "This," a GEC scientist says, tapping the device with his pen, "is what you claim produces 10 kilowatts?" "We don't claim, sir," Randall replies, calm and precise. "We've measured it. It produces more than 10 kilowatts. Our test equipment couldn't handle the full load." "It's crude," another engineer mutters. "It is crude," Boot adds, "but it's not fragile, and it works." A demonstration is arranged. The GEC team wheels out their finest, most advanced klystron. It's a beautiful piece of engineering, all delicate glass and complex wiring. They power it up. It painstakingly generates 100 watts. The committee nods, impressed. This is the state of the art. Then Randall and Boot wheel in their brute. The copper block, the giant magnet, the thrumming power supply. They turn it on. The device screams to life. It instantly produces 15,000 watts. The fluorescent lights in the ceiling flicker. The GEC team's antenna probe, brought near the output, melts. The room is silent. The war has just changed. The validation is total, but it creates a new crisis. It is August 1940. The Battle of Britain is raging. Britain does not have the industrial capacity to mass-produce this revolutionary device and build the planes, ships, and guns it needs to survive. Churchill's government makes one of the most momentous decisions of the war. They will give the invention away. In total secrecy, the Tizard mission is launched. A delegation of British scientists, led by Sir Henry Tizard, travels to a neutral United States. In their luggage, locked in a plain black deed box, is a single precious cargo, the cavity Magnetron. At a secret meeting at the MIT Radiation Laboratory, the Rad Lab, the British team unveils the device to their astonished American counterparts. The Americans had been working on 10-centimeter radar for a year. Their best result? 50 watts. The British present a device no larger than a dinner plate that produces 1,000 times more power. An American scientist later calls it the most valuable cargo ever brought to our shores. American industry, a sleeping giant, awakens. Bell Labs, Raytheon, and the MIT Rad Lab pounce on the design. Within weeks, they are refining it. Within months, they are mass-producing it by the thousands. The results are immediate and devastating. The new AI, Airborne Intercept Radar, small enough for a fighter, is installed in British Beaufighters and Mosquitoes. Flying Officer Alistair Finch, our blind pilot, flies again. But now, in his cockpit, there is a small, green glowing screen. On a night in 1941, he hears the same call from Vector. "Bandit, range 4 miles. But this time, Finch looks at his scope. A tiny, brilliant green blip appears. "Vector," he says, his voice cold and steady. "I have him. Warlock, engaging." He maneuvers, the blip growing brighter until he is 600 feet behind the unseen bomber. Tally-ho! He presses the cannon triggers. The night is lit by the explosion. The blitz is broken. In the Atlantic, the H-2S radar, built around the Magnetron, is installed in patrol bombers. U-boats, surfacing at night to charge their batteries, are suddenly, inexplicably attacked from the black sky. Admiral Karl Dönitz, commander of the U-boat fleet, writes in his war diary a tone of pure confusion and dread. The enemy has, by some new means, robbed us of our invisibility. The Battle of the Atlantic turns. The crazy idea of 2 men in a university lab has given the Allies eyes, and with those eyes they are winning the war. The legacy of the cavity magnetron is absolute. It is not just one invention among many. It is the central, decisive piece of technology that pivots the conflict. It is installed in everything. Naval radar, based on the magnetron, allows Allied battleships to conduct pinpoint gunnery in total darkness and thick fog, sinking enemy vessels that never see them coming. Bomber Command's Pathfinders use the H-2S radar to see the ground through solid clouds, identifying rivers, lakes, and city blocks to drop their markers with devastating precision. It is even the key to the war's final, most terrible weapon, The radar altimeters that detonate the atomic bombs over Hiroshima and Nagasaki are precision fused by tiny magnetrons. The device built to save Britain ends up shaping the entire post-war world. And what of the inventors? John Randall and Harry Boot are given an award by the King for their invention, but they are not men who seek the spotlight. Their names do not become household words like those of generals or politicians. After the war, they quietly return to their first love, academia. Sir John Randall uses his new prominence to found a laboratory at King's College London, but he doesn't study electronics. He moves into the new field of biophysics, using his knowledge to help build the microscopes that would allow others, like Watson and Crick, to discover the structure of DNA. Harry Boot also returns to physics, working in research until his death. They were humble, brilliant men, academics who, for one brief, desperate moment, were called upon to be the war's most important weapons designers. Their invention, however, has a strange and peaceful afterlife. In 1945, an American engineer named Percy Spencer, working at the Raytheon Company while testing a new magnetron design, notices something odd. He stands near the active device, and the chocolate bar in his pocket melts. Intrigued, he tries again with popcorn kernels. They explode. The next day, he brings an egg. It cooks so fast it explodes in a colleague's face. The high-power microwave generator designed to hunt and destroy is also a phenomenally efficient way to heat food. Raytheon patents the idea, and in 1947 they released the first commercial radar range. It is 6 feet tall, weighs 750 pounds, and costs $5, but the lineage is direct. The small cavity magnetron, humming quietly inside nearly every kitchen in the modern world, is the direct descendant of that crude, wax-sealed copper block built in a desperate lab in 1940. It is a sword beaten into a plowshare, a piece of wartime fury domesticated into a tool of convenience. It's a reminder that the greatest leaps forward often come not from the centers of power, but from the fringes, from crazy ideas that hold just enough truth to bend reality. What other forgotten stories of courage should we tell? Comment below.